Number of 1 bits. Want to impress interviewers with a classic bit manipulation trick? Number of 1 bits, or Hamming weight, is a pattern mastery 100 must-know and a favorite for roles at Google, Microsoft, and anywhere you work close to the metal. This deceptively simple problem reveals who understands how numbers are stored and manipulated at the binary level. Get this one right, and you'll be ready for any bitwise brain teaser they throw your way. Let's break it down. Given a 32-bit unsigned integer, your job is to count how many ones are in its binary representation. For example, the input here is a number where only a couple of bits are set, and we need to count all of them to get the answer. Now, let's assess our approaches. You could shift and check every bit, but that's up to 32 steps for every number. Can we do better? Yes. With Brian Cunningham algorithm, we repeatedly flip the least significant 1 bit to 0 using n and n-1. This clever trick only loops as many times as there are 1 bits, lightning fast for sparse numbers. Here's the structure. Start a count at 0, while n is not 0. Set n equals n and n-1 to clear the lowest set bit. Increment count. When n is 0, count holds your answer. Let's try to implement it using solution 1. This defines a function called Hamming weight that takes a number n. Our job is to count how many ones appear in its binary form, like counting how many on switches are turned on. Here we create a counter named c and start it at 0. This will store how many 1 bits we find. This loop runs exactly 32 times, once for each bit in a standard 32-bit integer. Because the loop count is fixed, the time complexity is 01, meaning constant time. It never grows with input size. This line checks the last bit of n. N and 1 isolates the rightmost bit. It's like shining a flashlight only on the final switch. If that bit is 1, we increment c because we found an on bit. Now we shift n 1 bit to the right using an unsigned right shift. That basically moves every bit 1 position over, dropping the bit we just checked, and bringing the next bit into the last bit spot. It's like sliding a row of switches so the next switch lines up under our checker. This closes the loop. After 32 rounds, we've inspected every bit. Now we return c, which is the total count of ones we found in the binary representation of n. And this closes the function. And that's how this algorithm works. It first sets up a counter and a fixed 32-step loop, then checks the last bit each time, adds to the count when it's 1, and shifts right to inspect the next bit. Efficient, simple, and elegant. Let's test our function using this input, n equals 11. This number represents the integer whose binary bits we're analyzing. We want to count how many ones appear in its 32-bit binary form. Here's why the solution works. We check the last bit of n over and over. N and 1 tells us if the current last bit is a 1. If it is, we increment our counter, then we shift n to the right using n equals 1, which moves the next bit into the last bit position. We repeat this for 32 steps to cover all bits. For 11, the binary form is 1011. That has 3 ones. 1, 0, 1, 1 total 3. And that's exactly what our program outputs, 3. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully counts the number of set bits in the integer. Efficient and accurate. Now let's try another implement approach using solution 2. Here we define a function called Hamming weight that takes a number n. Our goal is to count how many ones are in its binary form, like counting how many on switches are flipped on in a row of switches. Time complexity, OM, where m is the number of set bits, because we loop once per 1 bit. We create a counter named c and start it at 0. This will track how many 1 bits we've found so far. This loop keeps running as long as n is not 0. In other words, keep going until there are no ones left to remove. This is the magic step, Brian Cunningham's trick. When you do n 1, it flips the rightmost 1 bit in n to 0, and turns any trailing zeros to 1. Then n equals n 1. Keeps everything the same except it clears that rightmost 1 bit. So every loop removes exactly 1 on switch from n. That's why the time complexity is OM, 1 loop per set bit. Since we just removed 1 bit, we increase our counter by 1. Basically, yep, we found another one. This closes the loop. Once all 1 bits are removed, n becomes 0, and the loop stops. Now we return c, which is the total number of ones we counted in the binary representation of the original number. And this final line closes the function. Done. And that's how this algorithm works. It first starts a counter at 0, then repeatedly removes the rightmost set bit and counts how many times it can do that until the number becomes 0. Efficient, simple, and elegant. Let's test our function using this input, n equals 128. This number represents the integer whose binary bits we're checking, and our goal is to count how many ones appear in its binary form. Here's why the solution works. Each loop removes one set bit from n. We do that with n equals n1, which clears the rightmost one bit every time, and we increment c once per cleared bit. For example, 128 in binary is 10 million, that's a single one followed by zeros. Do n, 1. 127 is 0111111. Now n, 1, becomes 10 million and 0111111 equals 0000000. So in just one step, n becomes 0, meaning we cleared exactly one set bit, so c equals 1. And that's exactly what our program outputs, 1. This confirms that our code is working correctly and passes the test case. So, our implementation is correct. The algorithm successfully counts the number of set bits in 128 by clearing 1 bit per loop, efficient, accurate, and reliable. Alright, let's wrap this one up. This problem was all about uncovering the hidden ones inside a number's binary form, a perfect mix of logic and bitwise precision. Breakdown recap. We began by understanding that the task is to count how many bits are set to 1 in a 32-bit integer. It's simple in concept. Look at the binary version of the number and figure out how many ones are present. Assess recap. Next, we compared approaches. The straightforward way is to check each bit one by one, but that's not very efficient. Instead, we turned to Brian Cunningham algorithm, which smartly removes one set bit at a time using n and n1. This drastically reduces the number of steps, especially for numbers with few ones. Structure recap. The logic flow was clean and minimal. Start with a counter, repeatedly clear the lowest set bit, and keep counting until the number becomes 0. When it's done, that count gives the total number of 1 bits. Implement recap. We implemented this on LeetCode, and the solution ran smoothly without any errors. Check recap. After testing the code on multiple inputs, every test case passed, confirming the efficiency and accuracy of the approach. The key takeaway here is the elegance of Brian Cunningham's algorithm, a reminder that understanding bit-level manipulation can turn a brute force task into a lightning-fast solution.